Hey guys, how's your day going?
Going good. How's your day going?
Doing okay. I know you didn't ask, but my thumb's like feeling a little bit better because I skipped physical therapy exercises yesterday, but maybe I shouldn't. Anyway, you never know. I'll eventually be able to grip a jar again. Okay, so where we stand is we're today supposed to talk about chapter three, section three, regression trend lines, but I think maybe it'd be a good idea to spend a few minutes, not too long, but a couple minutes talking about any administrative questions you might have related to the exam before we move further forward, or anything that sort of came up from the homework exercises that you turned in, and then the answers have been put online. Any quick questions? Okay. That is not a quick question. That's not a question at all. Okay, so if I remember, two class sessions ago, we talked about correlation as a way of measuring the amount of linear association between two variables, quantitative variables, in the context of a scatter plot. So maybe I'll start by showing you an example data set. And okay, and this is a data set that I think really works very well for a lot of majors, again, because you can relate to it in some ways. But to be honest, it's one of those things where, again, I think data sets that everyone can sort of say, oh, I sort of get it. Those are helpful data sets. So let me share a screen and that guy share. And these are data on a collection of skyscrapers or buildings that are termed skyscrapers built in the US during a long time period. You can see like 1920 was the earliest or one of the earlier buildings here, and it goes through buildings built like 1989 or so. So it's missing some of the really tallest buildings in the world. These are just in the U.S. And we've got information about the number of floors the building has in it. And unlike in some countries, we're just counting the number of floors here, and not sort of how they're numbered. Like I guess in the U.S., sometimes there's the ground floor G, and then you go up to two or three or four. In some countries, you might have the ground floor being labeled G, and then the one above you is labeled the first floor. We're just counting the number of stories that the building has in it, the number of floors, and that sort of handles situations like in the U.S. where we sometimes have buildings without a 13th floor for a variety of reasons, or there may be a lack of eighth floors in some places, and so because of that, we're just going to count the number of floors and then the height of the building, and this is in feet. Okay. So let's look at a scatter plot and a correlation. And the way we talked about that recently was under analyze, multivariate, multivariate. Okay. We could see if there's a relationship between the height of a building and then the number of floors that the building has in it. Perhaps we could talk about predicting the height of a building based on the number of floors, and that would be in this graph over here, where the number of floors is displayed along the x-axis, 20, 30, up to 100 or so, and then the height of the building, or shoot, maybe it's sort of naturally the other way around in some contexts, maybe based on the number of the height of a building. You're just looking at it and you say, oh, that's 1,000 feet tall. You're thinking, how many floors would it have? Maybe about 70 or so. So we think that there is a relationship. The correlation here is, in this case, pretty strong. 0.95 is noticeably, in this case, linear and very clear, the pattern. Another way to try to describe that relationship graphically is well with the scatter plot, but we can produce it with Graph Builder. And Graph Builder, as we've tried before, the number of floors may depend on the height, or no, the number of floors may predict the height of a building. I think that makes more sense. I think most people say, okay, how many floors do you want your building? And let's design the building to be the right height. rather than saying, how tall do you want the building to be? Okay, now how many floors do we jam into it? And I see there's this positive trend. You could even say it's linear in shape. And the question is, what is the XY relationship? If my goal were to predict a value Y from knowledge of its X, and I've got these scatter plot data points here, how could I come up with an XY trend line? And when I say line, I'm thinking, well, there's an equation for every line. And if it's a straight line, I would say Y is, and I'm going to go with my way of writing things, A plus B times X. Some people write Y as MX plus B. I really don't care for that. That is a straight line relationship. And if I were to draw that trend line in a scatter plot, I'm thinking I could, as long as I draw it straight, well, and that's not necessarily the best line that I drew in, but it is a line. It tells us a way of predicting a Y. So I'll call that Y hat, my prediction of Y, based on the intercept and slope, and then also then the value of X, in this case, the number of floors that the building has in it, okay? And for any particular value in my data set, and I'm going to go with 70 floors, I'm going to say, okay, for 70 floors, there is a data point with exactly 70 floors, and I'm going to go up to that guy, and I can read across and find its actual height, but there was the predicted height, if you will. My Y hat value will allow me to predict the actual Y. And if I'm doing a good job, my predictions will tend to be quite close to the reality. Okay, I'm thinking what we could do is try to discuss how far off our predictions will be. And I'm thinking one way of describing the amount of error in our prediction is what we'll call SSE, for the sum of squared error. Okay, and we're going to get the phrase least squares from this. And the SSE value, SSE, for a data set and a trend line is summing across all of the data values. I goes 1 up to n. The actual value of Y, okay, yi, I guess I should say, minus A plus B times xi. That is my Y hat value. So here we go, Y hat for that ith value. How close was the actual to what I would have predicted it would be based on my choice of trend line, my choice of A and B. Now I'm going to make a claim here. And that claim is some lines are better than others. And the lab will ask you to explore this a little bit. But I'm sort of thinking, if I had shown you, oh, darn, I removed my equation. If I'd said, here's my trend line, you would have said, that's a horrible trend line, because it's well above where the data points are for the lower data points, and it's well below where the data points are for the higher data values. But across the entire data set, these vertical errors of the data points relative to that trend line, those are going into SSE. SSE equals the sum of the squared prediction errors. And if I'm predicting a height and there's an actual height, those prediction errors are always in feet minus feet. These are vertical errors. Now, if I remember looking at my SSE equation, it's equal to summing across, again, yi minus A plus B times xi squared, and I goes 1 up to n. I guess if I wanted to write this out in terms of a quadratic, in terms of A and B, I could. And the claim here, and all of you have been required to take at least one calculus class, but not necessarily all of them. But I'm going to speak as though you've taken multivariate derivation or derivatives before. And I'm going to say, let's take the partial derivative of SSE with respect to A, and we'll set that equal to 0. And we're also going to take the partial derivative of SSE with respect to B and set that equal to 0. And because I'm going to set both partials equal to 0, and shoot, this is a value which is quadratic and increasing, I guess there's an A and a B, which will cause SSE to be minimized. If I set those partials equal to 0, that's a way of finding that minimum value, the A and the B that give us the minimum SSE, or if you will, least squares. And so that's really what we're going to be doing here. In the lab, you're going to sort of poke your way through doing this by hand. And I'm just going to make a bold claim here, okay? The bold claim is that the slope B that minimizes SSE is going to be the correlation between X and Y. And if X and Y have correlation measuring the amount of linear association, it makes sense that it would be in here somewhere, times the standard deviation of the Y variable divided by the standard deviation of my X variable, okay? So if I tell you R, SY, and SX, you could find the slope rather quickly. And similarly, I'm going to tell you A happens to be Y bar, the average of the Ys, minus my newfound slope B, I just found the slope over on the left, times X bar, okay? That tells me essentially if I know X bar, Y bar, SX, SY, and R, between those 1, 2, 3, 4, 5 numbers, I can calculate the intercept and the slope. This first equation gets us the slope, and the second equation basically takes our trend line with the right slope and raises or lowers it until we have it going through the intercept that will minimize the sum of squared errors. If my trend line is too high, essentially you're thinking, well, that looks like the right slope. Maybe we should lower the trend line. We should adjust A. Our equations here will, however, just tell us exactly how to do that. Okay, so let's go ahead and try this with this data set. I'm going to calculate the correlation, the standard deviation of X and of Y, the mean of X and of Y. We'll write those down. We'll do this by hand, and we'll see where we get to. Okay, so what do we have over here? Correlation, let's get that guy. Under Analyze Multivariate Methods, Multivariate. Let's find the relationship between the height and the number of floors, or the stories. Click OK. And I have a correlation of 0.9506. So I'm going to write down R here is 0.9506. Okay, so let's move that one off to the side because it's now in the way. And with my two variables, X and Y, the height, Y, and X, the number of floors, I need the means and standard deviations. So under Analyze Distribution, I could find information about the height and the number of floors. And I'm going to have then, well, darn it, stack those up and I could read them. And I don't need to look at the picture, but I need to look at over here off to the left, the means and the standard deviations. And shoot, I dragged it off the screen. So the top one is height. That's my Y variable value. So I'm going to write Y bar is 546.3. X bar, that's the mean of the height, and that's the Y bar is the mean of the heights, and X bar is the mean of the number of floors, 40.38. I'm rounding a little bit. I apologize if you don't like to round as much as I do. The standard deviation of the Y's, the spread of the Y's is the 186.2. The standard deviation of the X variable values is 15.67. Okay. Notice here I'm keeping about the same level of precision, 1, 2, 3, 4 digit precision throughout all of the terms that I've got. So ultimately, my answer should be accurate to within about 3 digit precision, perhaps. Okay. So let's find our intercept and slope. Slope first, and let's go with the slope B is R times SY over SX. Here we've got 0.9506 times the standard deviation of the y's. Well, that's 186.2 over the standard deviation of the x's, 15.6. Now, I don't do 4-digit multiplication, 15.67, and I don't do 4-digit division in my head so very well. So I'm hoping one of you could find this number for me. I'm hoping it's like 11.3 or so, but I don't remember all the details. So I'm going to write it as 11 point something, and one of you will hopefully tell me 11 point what?
11.88.
88?
Yeah, 88257, and then it goes on.
Yeah, I'm thinking I may have written down something incorrectly here, because that is not what I was expecting y'all to tell me. And I've done this example so many times, I should be
Oh
getting.
wait, I just did the division. I didn't multiply it. Hold on.
Okay. Woo.
11.29.
11.29?
Yeah,
0.29 what? Haha.
55.
Okay, so 11.2955, I'll call that 11.30. And if you'll want to be more precise, 2955, I'm good with that, but I'm thinking 11.3-ish. Okay, y'all good so far? Yay. Okay, so the intercept then is going to be something that is hopefully easy to get, because it's a little bit quicker. A should be y bar minus b times x bar, and I've got my b now. 546.3 minus 11.30 times then x bar. That's 40.38, and that should equal let's think 50 or so. So like, notice I said 50 or so, and then I had like a question mark in my. Tell me the number here. 75. I don't know. What is it?
90.
90. Hold on, that seems suspicious. And indeed, 90 seems really suspicious, because 400. Okay, maybe about 90. Yeah, 90. Okay, so 90 point what? Give me 1 digit extra.
On the dot.
On the dot. Okay, so 90.0. Okay, I'm happy with that. So I'm claiming the trend line here, y bar, y hat, I apologize, y hat, the trend line is 90 feet plus 11.30 feet per x. Okay, and notice that I wrote it out and said it that way. In fact, shoot, I think that even suggests an interpretation of the slope, an interpretation of the intercept. For each additional floor taller a building is, for each 1 unit increase in x, the slope tells us how many more y on average we're going to have, 11.3 feet per floor. And this is why this is a great example, is Cal Poly has like a construction management major, and all the CM students, like when you get them in a class and you walk them through the example, they're like, yeah, that's about right. And I'm thinking, I look up in most buildings at Poly, and I'm thinking, okay, that's like 8 feet or so. Not all of them, but the typical 8-foot ceiling. And they're saying, oh, no, you got like the girders between consecutive floors, and you got duct work, and you got sort of a conduit running there, and then pipes, and they say it's going to be 11.3 feet per floor. And so that checks out as at least construction management major approved. Architectural engineers and architects also say, yeah, that works. Okay. But what the hell with that 90? The intercept is always given the interpretation, the typical value of y when x is 0. So let's think about it in the context of this example. For skyscrapers, because you have to be a skyscraper, whatever that means, a lot of floors in your building, to even get into this data set. So for really, really, really tall buildings, on average, if they have 0 floors, they're 90 feet tall. And so I'm thinking that just makes no sense at all. They're not going to be 90 feet tall if they have 0 floors. That's not a skyscraper. That's like a no floor building. That's not even a building. Maybe there's a parking garage underground, but there's nothing poking above the ground at all because there are no floors. Or is there? One thing that students in construction management in other areas tell me is like, oh yeah, if it's a skyscraper, typically when you walk in, the first floors, you look up and there's like, 20, 30, 40 feet of airspace above you before you hit floor 2. Okay. And similarly, if you go to the top of those buildings in New York City, the really tall ones, you look on top, there's air conditioning units that are 10, 15 feet tall. There's towers, and those towers often have cell phone stuff in them. So the typical height of a building isn't just based on the number of floors. There's extra stuff added in on top of that. Okay, any question about interpreting the intercept and the slope in the context of a regression? Okay, well, let's go ahead and verify that indeed we get these exact same answers with this same data set using JMP. So let's clear that and go back to the method that ultimately you'll be using in lab today. Under analyze fit y by x, we're moving from analyze distribution into fit y by x, looking for relationships between x and y, or trying to describe the nature of those relationships. Does the height of a building depend on the number of floors, or how does the height of a building depend on the number of floors? I click OK. My magic graph is calculated for me. Under analyze fit y by x, you never sort of get the analysis completely done for you, but it shows you a picture of everything that's sort of going to tell you, oh yeah, that's about the right sort of thing I want to do. And then you're asked, okay, now specifically, what do you want? Add in a line for me. Fit a line. Okay, and it's going to give you the equation for the line right up front. 90.3 plus 11.292375 times the number of floors. I'm going to claim that we sort of confirmed these two numbers because, probably rounding error. I chose to use 4-digit precision. The software is going to be probably using 8-digit precision. And so I trust it over me. But at least what we did checks out as viable or plausible. Any questions about how to do this so far? Okay. Well, I want to sort of get into one additional question because I think it's sort of a fun one. And that is based on the brain weight of a critter, could we predict the gestational period of that critter? Like how many months, okay? Or better yet, brain weight and body weight. We'll go with those guys. Brain weight, and this is in, shoot, what is the unit of this? Well, let's look at human, because maybe human will help us. Human being, 1,300, so that's probably in grams. So brain weight in grams and body weight in kilograms. So brain weight in grams, body weight in kilograms. I think probably larger critters have larger brains, not all of them. Well, on average, that's probably what we would be seeing. Let's look at a scatter plot of that situation. And again, your friend Graph Builder is a good way to go. And I'm thinking maybe we should have brain weight on the y-axis and body weight on the x-axis. I'm not telling you that's for sure the right way to go, but it seems plausible to me. And this looks hard to say that that's linear. Do y'all say, oh, look, linear? No, I'm thinking most critters aren't as big as like elephants and blue whales, okay, or humans here. But it seems as though this is a critter which has a very large brain weight relative to its body weight. Okay, so I'm thinking something smart. I don't know what it is, but it seems like it'd be smart. Humans, maybe our brain weight compared to our body weight is, oh, no, that's a body weight 1,400. That's not an elephant. That's like a horse or something. Okay, so humans are like body weight down here. Okay, maybe this is a human. No. Maybe that's the human. Yeah, human here. So what the heck is that critter? Okay. Well, I guess I could highlight it and find out which critter it is. And let's see who is, relatively speaking, a bit smarter than us. Dolphins! Compared to the body weight, dolphins have brains that are pretty darn big. But I'm thinking I don't feel comfortable using this scatter plot to say here is the relationship between X and Y, brain weight and body weight. Again, graphically looking at brain weight as a function of body weight. I'm not saying I'm seeing a linear trend. That graph here, maybe I'll get rid of it. But I am thinking there is probably something going on, but we're overemphasizing graphically these few critters that are just really big. And we're de-emphasizing all the rodents. There's tens of data points way down here that we can't even see because they're all jammed in. If we stretch out our graph, we might be able to see it more easily. And just doing this doesn't really allow us to sort of view what's going on in this region. But I am thinking sometimes changing the way we measure things allows us to more cleanly and clearly spot what's really going on. So I'll just remind you of pH. Y'all remember your friend pH when you took chemistry? Okay, so some of you are nodding. Yeah, you remember pH. What is pH? It's the log of the ratio of anions to cations in a solution or something like that. And I'm thinking there's a log. Why not just use the ratio? Well, it turns out because the log is just much more convenient to work with for most contexts. In that same way here, sometimes a natural transformation of your X and your Y axes, you put them on the funny engineering logarithmic paper, you might see a trend as linear, which had not been clearly shown as linear earlier. So I'm going to show you how to walk your way through that sort of an approach. And if I click right here, right click on the axis settings, or right click on the axis somewhere, like the number 3000 here, I'm under axis settings. I can say, instead of showing me this in a linear fashion, what if you used a logarithmic scale? It's going to show the thing looking a little bit different, but it's going to have scale that goes from like 0.1 up to 10,000 on the y-axis. It's going to stretch out. Well, that doesn't look linear either, but maybe body weights similarly. I'm going to click on, in this case, right click on 2500 axis settings, and also make it logarithmic in its look. And I'm thinking that is really quite linear. So I feel comfortable saying the log of body weight and the log of brain weight have a linear relationship. So maybe if I just create the log base 10 of brain weight and the log base 10 of body weight, I'll be able to do my analysis. And well, ultimately, if we were to pursue the math far enough, you could work your way with anti-logs and find out you're going to get a, instead of a additive relationship, you'll have a multiplicative one. I'm going to create a new column here. Right clicking on an empty spot gives me a new column. I'm just going to call it the log base 10 of the brain weight. So I'm going to give it a name, and under column properties, I can say, let's create a new column based on a formula that uses data from other columns. So literally my log 10 brain weight, I don't have a formula yet, but log base 10 is one of the transcendental functions. So I'm going to use log base 10 of, then click the brain weight. I'm okay with that. And so something that was, and I'm looking for like a 100, so like 93 is close to 100, that should be about 2. Something that's about 10 should be about 1. Something that's 1,000 should be about 3. Yeah, so the log base 10 of brain weight, check. I click OK. Repeat the process. New column, log base 10 of the body weight. Again, under column properties, say, let's create a formula. And again, the transcendental function log base 10 is the one you're going to want to use. And log base 10 of what? The body weight. and this is body weight in kilograms. And we're now taking the log base 10 of that. So our log base 10 brain weight maybe is related to log base 10 of body weight. Let's go ahead and do our analysis, or the graph like before. And brain weight, log 10, brain weight, log 10 body weight. Indeed, it is the exact same graph that we had been looking at earlier that we were saying we wanted. So we're just taking the units, which now go from 0.1 to 1 to 10 to 100 to 1,000. We're just now using the power of 10, like a 0, a 1, etc., 2, a 3, as we go up. 3 being 1,000, 2 being corresponding to 100. But I could fit now a trend line through these data, I betcha. Okay, it looks linear. Let's find the correlation, find the mean and the standard deviation of each x and y, or just jump right into analyze, fit y by x. How does the log base 10 of the brain weight depend on the log base 10 of the body weight? I click OK. I have the graph reproduced for me, but now if I want to fit a trend line, you would say, aha, I know that the typical critter's log base 10 brain weight in grams is 1.013 plus 0.7192 times their log base 10 of body weight. Okay. So I could do a little bit of math work and figure out the XY relationship based on an assumption of linearity, but that works for my log base 10 data. So if our scatter plot isn't originally showing what looks like a linear trend, maybe transforming the X variable or transferring the Y variable will allow us to say, yeah, that's linear, and I feel comfortable fitting a straight line to describe the XY relationship of my transformed data. So the lab today walks you through doing two things. One is finding the least squares estimate. You and your group are going to try a couple different intercept slope combinations. You'll calculate SS error, and you'll indeed find that one of you is a little bit closer than another, and then you're going to do a guess and check operation to get even smaller SS error that eventually will have you compare that to what least squares does. Okay. Many students feel compelled to just jump to the conclusion, but no. Don't use regression. Don't use least squares until after you've done the guess and check several times across your group as a whole. And then it's going to deal with a data set where we're predicting the life expectancy of a country based on the number of televisions per person in the country. And you might think that sounds a little bit goofy, but I bet you the number of televisions per person has something to do with the wealth of a country, and the wealth of a country has something to do with the ready availability of medical care. Okay. And so in that regard, maybe even though you might not be able to predict the life expectancy of a country very quickly, we might be able to come up with a way of, based on just knowing how many TVs have sold in that country in the last decade and how many people live in that country currently, we might be able to come up with a quick guesstimate of the life expectancy based on just the number of TVs. Stranger things have happened. Okay. So because I sort of expected a few more questions from y'all on the exam in terms of administrative things, it didn't happen. But I don't want to go too much further into the material because this is a lab which, yes, you should do. And yes, you should do it before Monday of next week. But I would rather you spend time focusing on your exam. Okay, so we're at a good place where you should just bail out, go take a test, and be happy as a clam, knowing that there is another office hour opportunity coming up, but it will be right at 5:10 p.m. today. Any questions on anything before we close it up for the day? Okay, I'm going to close down or stop the recording, and then in